All right, let's get back to it. We were talking about the inverse trig functions. Let's continue. Last time we talked about the inverse sine. Let's try and do the same stuff for the cosine and the tangent. The inverse cosine, let's discuss that. Inverse cosine of x. I hope you remember the basic approach from last time. Last time we talked about inverse sine, and what is slightly complicated about this stuff is that sine, and cosine for that matter, are not one-to-one functions. So technically speaking, there is not an inverse for the entire sine x function. And to get around this issue, we take only a piece of it and take the inverse of that little piece. And for the sine, you try to take the biggest piece where it actually is one-to-one. I'm going to try and do the same thing for cosine. So the graph of cosine, everybody knows, looks like this. And that's the one that starts up here, so it's like this. That kind of a thing, right? And just like for sine of x, we are going to try to choose a piece where it is one-to-one. Unfortunately, in this case, you can't really start at the origin. If you start around the origin here, already it's not one-to-one. Even just like a very small area around the origin, say just that much, is not going to be one-to-one, right? So if you want to choose a piece, don't choose that piece. We have to choose a piece which is one-to-one. You have to basically only stay on the right side of the y-axis. So I'm only going to be choosing positive values because I can't choose both positive and negative, and it would be silly to start on the negative value. So I am going to choose, as far as a piece of this curve, maybe I'll use my little highlighter. Starting here, right? Can you see that? Yeah. And just go like as far as you can until you can't go any farther anymore. It has to stay one-to-one the whole time. So I think in terms of how far can you push this thing and still be one-to-one, you can make it all the way to there, right? You cannot start coming back up though, because then it won't be one-to-one anymore. So the piece which I'm going to use when I invert it is just that much. So this piece, only over here, starting at the top and coming down to there, and it does a little something like that. All right, this is not cosine inverse. This is just a piece of cosine, right? This is not the inverse yet. But maybe I'll label the axes. So up top is 1 and minus 1, right? Those are the y values. And then the x values, can someone say what's the x value over here at the end? Of course, it's 0 on the left. It is pi, yeah. Cosine goes down like that at pi. So this over here is pi. And right in the middle is pi over 2. And of course, x equals 0 on the left side. All right, so that's the piece. That's the original piece of cosine, and that's the one which I'm going to invert by doing this sort of reflection across this diagonal line, which is a little strange, but maybe it's a little easier in this example to think in terms of exchanging the x-axis for the y-axis. So the inverse, I exchange the x-axis for the y-axis. So in the original picture, the y-axis goes minus 1 to 1. That means in my new picture, the x-axis goes minus 1 to 1. And the original x-axis went 0 to pi, so my y-axis here goes 0 to pi. So it's all up here, right? That's what happens when you exchange the x and the y-axis. And then can you start draw the curve in? So the curve begins, on this picture, the curve begins at the minus 1 and then does this kind of, curvaceous kind of shape and ends up where the minus 1 is and the pi. So I begin, what? I put a minus 1 up there. That's bogus. That's foolish. It's plus 1. So my curve begins at plus 1. That's here. So when I draw this, the inverse starts over here, and then it curves over, cuts through the middle at pi over 2, up there. So it's going to do that, and it curves sort of in that direction, not the other way. And then through the middle and ends up there. This is supposed to be a symmetric kind of curved thing. Doesn't look great in my opinion. I'm going to try to beautify this a little. Doesn't really matter. Yeah, it's better, I guess. All right, anyway, this is the graph of inverse cosine, or arc cosine. Did everybody get the paper with the old checklist? All right, this is the arc cosine, or the inverse cosine, and I will just, you can tell this by looking at the graph. The inverse cosine has domain, you can see right there, -1 to 1, and the range is 0 to pi, right? The range is all the y values you can get out of it, and the domain is all the x values you can put into it. All right, great. Everybody got it? Excellent. All right. I'm always glad when nobody picks one of the columns, then I don't have to write that question. I realized maybe too late. It means like every week I gotta write like a question for every, it's basically I'm like writing a whole final exam every week. I don't like that. It's all right. I'm getting paid, so I can handle having to do stuff. All right. So, for example, what about how would you do individual values of this function? So something like inverse cosine of 1/2. What does that mean? Remember, the meaning of this is, it means what is the angle whose cosine equals 1/2. And in particular, it has to be the angle in this range, 0 to pi. So this, when you see that, how you interpret this is, which angle has, cosine theta equals 1/2, right? That's the question that this is meant to be answered. And specifically speaking, which angle in the range 0 to pi, right? You don't want to choose an angle somewhere else. But anyway, how would I do that? Well, cosine being 1/2, you just have to, for me, maybe you have some memorized unit circle things. The way that I remember this is those special shaped triangles, some of them have 1s and 2s on the sides, and the one that I'm thinking of in particular is this, or maybe I should write it this way around is better. Oh, that's pretty ugly. This is the 30, 60, 90 triangle, has a 1 and a 2 here, and this is the way you want it in order to get the cosine to equal 1/2, right? So here, the cosine of this theta is 1/2. And what is that angle? Yeah? That's a 60 degree, also known as pi over 3, right? In radians. I'm always going to say this in radians. Okay, great. So this is pi over 3. And pi over 3 really is in this range from 0 to pi. So that means the inverse cosine of 1/2 is pi over 3. Great. All right. If you remember these values in a slightly different way than I do, that's fine with me. I just sort of have all these triangular shapes memorized, I guess. What about inverse cosine of -1/2? So this is similar, only I need a triangle where the cosine ends up being -1/2. That one, so the way that I would think of it is, it's basically this, but I want the adjacent side to be -1 instead of 1, which I would draw as the same triangle but oriented over here. So now it's -1 here and 2. And then what's the angle here? That would be this angle as measured from there. This is, I don't know in degrees, 120 degrees or 2 pi over 3 radians. All right, that's this angle here. So inverse cosine of -1/2 is 2 pi over 3. All right? And as was mentioned last time, you know, there are other angles whose cosine is negative a half. Like you could have also done this triangle. This also has -1 and 2 here, all the way like that. That angle in radians would be, it's pi, which is all the way across, and then plus another pi over 3, so this is 4 pi over 3. But that would not be the answer to this inverse cosine, because the inverse cosine function, its range is only 0 to pi. So you cannot get an angle outside of that range, 0 to pi, and 4 pi over 3 is outside of the range. So you wouldn't say that as the answer to this inverse cosine. All right. I would like for you all to try. This is something that we did one example of this last time. There are formulas for this. Sine of inverse cosine of x equals what? And there's one for tangent. Tangent of inverse cosine of x. These are formulas I don't expect you to memorize, but it doesn't take much effort to come up with them. The basic strategy where you begin is inverse cosine of x is an angle where the cosine equals x. And the way to draw, you know, if you wanted to draw a triangle, I could label the sides to make the cosine equal x. Anyone remember I did this last time? How would I label the sides to make the cosine equal x? Yeah?
Would the opposite be 1? Or would it be, I don't know, x? The opposite
Yes.
side be x, and then, the adjacent side is x, and then the hypotenuse is 1.
Yeah, great. I want the adjacent to be x and the hypotenuse to be 1, because the cosine is the adjacent over the hypotenuse. So this picture represents an angle where the cosine equals x over 1, which is x. All right? I'll leave it to you to, how do you, so I'm trying to find the sine of this angle now, which involves filling in the blanks on the triangle so that you can find the sine and also the tangent. That's the second one. I'll give you a moment. See what you think. Yeah, so you want the sine of this triangle to be opposite of that.
Can you figure that out by?
You do the diagram here? Oh, you use the right triangle?
Yeah.
Yeah, so this squared plus that.
X squared is equals to
Well, it's x squared plus this squared. So I'll sort of into that. Yeah, you need to find that other side. Yep. And I take the sine. Hey. Yeah. Yeah, like that. Okay. Maybe this is a, you don't want
You said yes. You were like, oh, can you Are you good at kids? Are you good? They play like one guy upstairs, like the one guy. He always plays like this guitar.
all right. Yes. Excellent.
After you look, they were trying to show this kid how to play, like or something. It was just weird.
That's this side. This is
Okay.
C flat, and then you do the sine.
Yeah.
Like, just teach me one song.
So yeah, you know this side. Yeah. Great. And you do the tangent. All right, it looks like people are doing pretty well. I'm gonna see what I can do. You have to find the other side, the unlabeled side here. So maybe I'll just temporarily, I'll call it A. So you can do a little Pythagorean theorem to figure out what A is. I have determined that A is the square root 1 minus x squared. And then I can take the sine and the tangent of this angle. So the sine will be, so maybe I'll just put that here. This is square root 1 minus x squared. So the sine of this angle would be opposite over hypotenuse. That would be just this, right? 1 minus x squared divided by 1. But that's 1 minus square root of 1 minus x squared. And then the tan of this thing would be the opposite over the adjacent, which is this. Root 1 minus x squared over x. So these are formulas for those things. Like I said, I don't expect you to have these memorized, but they do come up sometimes, and in such a time, I would expect you to just be able to work it out. It'll only take you a few moments if you know what you're doing. Yeah?
So for this, when you're finding like the inverse of cosine, is that just you finding the A or whatever? Like, because I didn't see you do anything. You jumped straight to the sine once you found your missing side.
Yeah, so inverse cosine of x refers to some angle whose cosine equals x. So technically on this picture, like where is inverse cosine x? Inverse cosine x is that angle. This is a little strange.
Okay.
And then that angle is what I'm taking the sine of. And that's why I did this opposite over hypotenuse. Yeah. Great. All right, these are somewhat obscure formulas involving the inverse trig functions. Great. Can we talk about derivatives of the inverse sine and inverse cosine? Derivatives. Of course, everybody knows the derivative of sine is cosine. And the derivative of cosine is negative sine. Does that mean the derivative of inverse sine is inverse cosine? The answer is no, not remotely. It's not even close, actually. The derivative of inverse sine is something completely different. But we can still work this out. Anyway, where I'm going with this is, what about derivative of inverse sine and inverse cosine? So we're gonna cosine. Maybe I'll put this in a box. We'll fill in the blanks later. But it's nothing like you wouldn't expect. I mean, it's not just sines and cosines on the right-hand side of those equal signs. We can work this out without too much trouble, though. So how we would do this is, as usual, when we're dealing with inverse functions, I start with that, and then I'm going to write it the other way around by inverting. So instead of saying y equals inverse sine x, I can say sine y equals x, right? Because the inverse sine is meant to be the inverse of the ordinary sine. And then I'm going to do derivative on both sides. This technically is what they call the implicit derivative, where you have functions of x and y all mixed together, and you just take the derivative of everything. It's called the implicit derivative, which can be a little complicated in some cases, but this is an easy one. So I'm going to do the derivative on both sides. What do you get on the right side? This is especially easy. 1 is the derivative on the right side. Derivative of x is 1. On the left side, the derivative of sine y is cosine y, but leave a little spot in there. Leave a little room for the Holy Ghost, as they say. You have to also, because of the chain rule, multiply times the derivative of the inside, and in this case, what that looks like is this. Cosine of y is the derivative of sine of y, but because of the chain rule, I multiply times the derivative on the inside, which is dy dx. And now I can solve for dy dx, which is what I'm looking for after all. So dy dx, solving here, dy dx is 1 over cosine of y. And this is basically the answer for the derivative, although it's written in a especially inconvenient form. Cosine, I don't like to have a y in the answer here, because I want to write, like eventually I intend to copy something to this box. It shouldn't have any y's in it. So to deal with that fact, I'm just going to replace y equals inverse sine of x, right? So this is 1 over cosine of inverse sine of x, like that. And this could be your final answer. I mean, this is correct. That is what the derivative of inverse sine is. Although we typically don't write it in this way because this can be simplified. This is like what we did, I mean, what you all just did a few minutes ago, sine of inverse cosine. This is the other way around, cosine of inverse sine. But we did this towards the end last time, if you can see in your notes. The cosine of inverse sine of x is the square root of 1 minus x squared. So that last step that I did there is one of those same things about filling in the whole triangle and then taking a cosine of the inverse sine or whatever. All right? So this is the answer. That's what I'm going to put in my formula box here. 1 over square root 1 minus x squared. To me, it's kind of remarkable that you get an answer which has nothing to do with trig functions at all. It's just some vaguely polynomial-looking thing. That is the derivative of inverse sine of x. All right? Can I have you all try the inverse cosine? It should be very similar to all that. The derivative of cosine, inverse cosine of x. All right? You're going to do the same stuff that I just did, only it's, slight variations as you go. Got it started over here in case you're not sure.
Yes. Yeah. All right, everybody looks good here. Let me just try this real quick. So you start with y equals inverse cosine, and then you rearrange it. Cosine y equals x. Take the derivative on both sides. This becomes minus sine y times dy dx equals 1. And then I solve for dy dx. Divide the minus sine y. So dy dx equals 1 over negative sine of y. And y is inverse cosine x. So this is 1 over negative sine of inverse cosine x. And then that can be simplified. Sine of inverse sine is one of those ones that we just did a few moments ago. It is this, root 1 minus x squared. So my answer is 1 over minus root 1 minus x squared. All right, put that in the box. Excellent. All right, any thoughts about that? There actually is something a little weird about this. Inverse sine and inverse cosine, their derivatives are almost the same thing, which this seems strange to me. I expect, for using sine and cosine, you know, the derivative of the sine is the cosine, and the derivative of the cosine is the sine. I expect them to be some kind of like cyclical thing, but here they both have the same, basically the same. It's not exactly the same because of this minus sign, but they have essentially the same derivative. In fact, you can make it the same by just making one of them negative. So this is a fun fact. The derivative of inverse sine is equal to the derivative of negative inverse cosine, right? The difference between them is just a positive negative sign. But if you stick a negative into one of them, then actually those derivatives are the same. Does this strike anybody as strange? It strikes me as a little bit strange. What do you know if two functions have the same derivative? What does that mean about those two functions? Yeah? They differ by a constant. Yeah, it means they are basically the same function, only one is like a plus c different from the other one. Do you actually believe that though? Are these the same function? Just different by a plus c? This seems weird. It's actually weird but true. This is a fun fact. So what I'm saying is inverse sine of x and negative inverse cosine of x are the same. They just differ by a constant. They are, nobody said, like last time we talked about inverse sine, today we talked about inverse cosine. Nobody raised their hand and said, isn't that the same as what we did last time? And if you had said that, I would have said, no, that was sine last time. This is cosine this time. But they differ by a constant. Does this make sense to anybody? Perhaps, maybe I could just refresh our memory by drawing the graph. The graph of inverse sine was this. What was it? It went here to here. I want to make sure I get it right. It goes up, upsy daisies, like that, right? This is the inverse sine. And the inverse cosine is the one that we just did, which goes here, and it starts here and goes like this, right? This is the graph of inverse cosine, all right? What I'm saying is that sine, inverse sine, and negative inverse cosine are actually basically the same thing, just different by a constant. What would negative inverse cosine look like? Well, if you put a minus sign out front of this, it has the effect of vertically flipping this picture over. So negative inverse cosine, sorry, it's like downstairs now. It looks like I'm trying to draw this picture, but flipped over vertically. It now looks like that. And now, wouldn't you know it, really they are different by a constant, right? The graphs are the same, it's just one is shifted up from where the other one is. So this is really a true fact. This is something that to me is totally weird, but it is a fact. Inverse sine of x and inverse cosine of x are kind of the same thing, or at least I don't want to say that. But it is true. If you negate one of them, the inverse sine and the inverse cosine, these are the same. I will say different only by a constant. Strange but true. I'm presenting this as kind of strange because, of course, sine and cosine are not the same. But actually, from a certain point of view, sine and cosine are kind of the same. They're just like shifted horizontally. They are different from each other. They have the same shape. It's just they're shifted horizontally away from each other. So in that sense, it's not so surprising that The inverse sine and the inverse cosine are just shifted vertically from each other. It kind of all makes sense in some weird way. All right. Anyway, that's that. We were talking about derivatives. Right. Let's get back on track. Let's talk about the inverse tangent. We got 15 minutes left. Actually, the inverse tangent, also known as the arctangent, is kind of the nicest one out of all of these. And you'll see it's because of the technicalities about how you build it are nicer than the others. So this is called arctan, or tan with a little -1, the inverse tangent. If you ask me, anybody with any sense, if you ask me, what's your favorite inverse trig function? Without hesitation, I will say the inverse tangent. It's way better than the other ones. Why is it way better? It's because of the way that you have to create these functions by choosing a piece and finding the inverse. So we have to think about, what does the graph of tan look like? It looks like this. And then it has asymptotes here. And then another one of these guys, right? Etc. This is the graph. This is not inverse tan. This is just ordinary tangent of x. And what is nice about this one is it already comes in pieces. And so when it comes to, like, for all of these, we've had to say you just have to choose a little piece of it. Actually, there's kind of already a nice piece there waiting for us to choose, right? You can't take all of these branches, but you can just choose the one in the middle. So right here, we invert this part. All right? And just to be specific about where these asymptotes are at pi over 2 and minus pi over 2. That's because tan is equal to sine over cosine, and cosine equals 0 at pi over 2 and also at negative pi over 2. So you get asymptotes because of the dividing by 0. And we are going to invert only that piece. Let's see if I can draw a picture of the inverse then. I'm going to keep that on. So this is, over here I'm going to draw a graph of the arctangent, the inverse tangent. Now, on the original picture, I have x values of minus pi over 2 and pi over 2 are asymptotes. These vertical, what are these vertical asymptotes here? Become horizontal asymptotes in this picture because the whole picture is getting flipped over. So I have 2 horizontal asymptotes. All right? They used to be vertical asymptotes. So they are now horizontal asymptotes. These are horizontal totes. All right, I like to say totes because sometimes people don't want to write the whole word and they just write the first syllable of asymptotes, which is a little... I saw one time, I thought this was really funny, and I still remember it years later. Somebody, for some reason, it wasn't in this context exactly, but they were drawing a graph with asymptotes, and they wrote vert ass for that. I thought, that must mean something. Got that vert ass in there. There's only one S in the word asymptote, but people like to put the other one in there. Anyway, these are now horizontal asymptotes. And anyway, the graph now, so you can see in the original picture, it sort of begins at the -1 and goes up to the +1. So when you draw it here, it's like this, like that. This is the graph of arctangent or inverse tangent of x. It has horizontal asymptotes and goes like that. All right. The inverse tangent has is in general nicer function to work with, and maybe the principal reason for this is because of its domain. Can anybody say what's the domain of the inverse tangent? Yeah?
Negative infinity to infinity.
Yeah, it is if it, as an interval minus infinity to infinity. Or you could say all real numbers. Anyway, as a function, this is just a lot nicer to work with than the inverse sine, which has its domain is only -1 to 1, and the inverse cosine is the same way. You simply, there's some numbers you just can't plug into those functions. But this one, the arctan, is actually defined for all real numbers, so it's really quite a bit more convenient to work with. And the range is minus pi over 2 to pi over 2. And this should be an open interval because pi over 2 is not ever achieved by this function, right? It's an asymptote which the function approaches, but there is no value equal to pi over 2. They just approach pi over 2. So this is a open interval here. All right. So the arctangent, you can plug whatever number in you like. The inverse sine is like you have to be careful about things which you don't have to be careful about for the inverse tangent. All right. Can we talk about the derivative? We got 10 minutes. We can do the derivative of the inverse tan. I'm going to do it in the same way. So we would start with y equals inverse tan of x. And then we would write it the other way around, right? Tan y equals x. Take the derivative on both sides. Anyone remember what is tan? The derivative of tan? This is a lesser known, but I'm sure somebody knows.
Secant squared.
Yeah, this is the secant squared. So this is secant squared of y times dy dx. This is exactly like the examples we just did for sine and cosine. And then I'm going to solve for dy dx by dividing by secant squared. 1 over secant squared of y. Secant squared is, remember secant is 1 over cosine, right? So what I have here is actually 1 over cosine. So this is the same as cosine squared of y, because the secant is 1 over cosine of y. But anyway, I'll plug in the y here. This is cosine squared of y, which is arctan x. All right? And you could just leave it at that. I mean, that's a correct answer, although it's weird. As we have in the other examples, we can simplify this. So how do we do cosine squared of inverse tan of x? First of all, I would rewrite. I, in general, don't like writing cosine squared. I find it a little confusing. This doesn't mean cosine of cosine. It means cosine of this, the whole thing squared. So I'm going to write it that way. Cosine of inverse tan x, the whole thing squared, right? That's what cosine squared means. I find it much clearer to write that last way that I did there. But anyway, how do you find cosine of inverse tan x? You make one of those triangles, just like we did a couple of times earlier today. So I'm going to make a triangle here. I want to make this triangle so that its tan is x. Anyone want to suggest how should I label the sides then? I'm only going to label 2 of them. I want the tan to be x, yeah.
Opposite would be x and adjacent would be 1.
Great. The opposite should be x and the adjacent should be 1. That way the tangent of this thing is x over 1. I need to find the third side so that I can take the cosine of that. The third side, this is a little easier, I guess. Just the straight up Pythagorean theorem, 1 squared plus x squared is the third side squared. So this is square root 1 plus x squared, all right? And now we can do the cosine of that. It is, so just continuing where I had before, the cosine of that stuff, of course, it's all going to be squared, but the cosine of this angle is adjacent over hypotenuse. So it's 1 over that square root thing. All right. And we can simplify this. The squaring can go into the denominator, and then it will cancel the square root. So the whole thing is just 1 over 1 plus x squared, which is really arctan is so awesome, it even has a nicer derivative formula than the arcsine and the arccosine. All right, so I will put this in a little box. 1 over 1 plus x squared, like so. That is the derivative of the arctangent. It's a nice formula, yeah.
Is arccotangent just the negative of this?
I think it is. Although it's not obvious that should be the case.
All the cos are the negatives, like sine goes to cosine is negative, and then it's cosecant.
Yeah, when you take the derivative, generally, the cos make it negative. But
Yeah, I wouldn't say, when you ask me a question like that, I'm wondering, is there some good reason why that should be true? And I think the answer is, well, at some level there is, but there's not an obvious reason why it should be true. But yeah. Yeah, great. We got 5 minutes. I had just a few quickies of practice with these derivatives. So these are fairly straightforward if you know the formulas. How about what's the derivative of inverse tangent of negative 8x? So this is just a matter of using the formula in the box together with the chain rule, right? We need the chain rule in this case because I have some stuff inside of the inverse tan. But anyway, the way we would use it is, first of all, just plug directly into the box where instead of x, I have negative 8x. So it says 1 over 1 plus. And now instead of x, I'm using minus 8x. So it's like that, all right? That is just directly plugging into the box with negative 8x instead of x. And then I got to do the chain rule. So I go times. And now what I'm putting here is going to be the derivative of the inside, right? And what's that in this case? Negative 8, yeah. I'll put it in parentheses so it's clear. Times negative 8. Yeah, great. How about, let's do another one. How about derivative of inverse cosine of root x? I hope you remember the formula. We'll just write them again. The derivative of inverse sine is 1 over square root 1 minus x squared, and the cosine is the same, but it's negative. So can we do the one I set up there? Cosine inverse of root x. We should plug directly into the formula in the box with root x instead of x. So this becomes 1 over minus root 1 minus root x squared, like that. And then I go times the derivative of the inside. Can anyone say what that is? Yeah?
Is that 1 over 2 root x? Or,
Yes. Yes, it is. I was going to say it like this.
okay.
You're doing some fancy simplifying. But yeah, this is the same as 1 over 2 root x if you prefer. I think it's a little clearer to write it this way. Yeah, great. And of course, you can simplify this a little bit if you wanted to, but I don't care about that, as always. All right, one more. How about derivative of inverse sine of 4 to the power x? I'm mixing it up. 4 to the power x is, we talked about that kind of a thing last time. So I do the formula for the inverse sine, which is in the box there. 1 over root 1 minus, here, 4 to the x squared. So that is directly plugging into the formula in the box. And then, as before, times the derivative of the inside. Anyone remember what's the derivative of 4 to the power x?
Is it x4 to the power of x?
No, there's a special rule when x is inside the exponent, which we talked about. Yeah, this we did last time. 4 to the x times ln 4. I'm mixing up the two topics. That's what they call using the whole buffer.